Welcome to Math Club in Learning Home.
Hello students, hope you all are doing well. In the previous lecture we discussed inverse Laplace transforms and some properties of inverse Laplace transforms, and after that we used method of partial fractions to find inverse Laplace transforms of different functions. In today's lecture we are going to discuss some more properties of inverse Laplace transforms that will help you to find inverse Laplace transforms of many functions. So let us start our lecture by taking our first property. The first property we are going to consider is the change of scale property. Which says that if you have inverse Laplace transform of a function, say f of s, and if this is given by f of t, say, then we can find inverse Laplace transform of the function f of as. Means you are multiplying or dividing by a scalar a, and this will be given by 1 over a f of t over a, and this result directly follows from the result of Laplace transforms. As you know that if the Laplace transform of f of t is f of s, then the Laplace transform of f of at is given by 1 over a f of s over a. This we have already used the change of scale property for Laplace transforms, and if you invert here, that is, you take the inverse Laplace transforms, then you get the inverse Laplace transform of 1 over a f of s over a will be equal to f of at, and since L inverse is linear in nature, you take this a to right side, and this will imply that the inverse Laplace transform of f of s over a is equal to a into f of at. And it is very much clear that if you replace a with 1 over a, then you will get this result. So let us use this result to find inverse Laplace transform of one function. So let us try to find the inverse Laplace transform of 2s over 4s square plus 9 using inverse Laplace transforms of s over s square plus 9. So I am going to derive the inverse Laplace transform of this function from the inverse Laplace transform of this function s over s square plus 9. So I am taking this function as my f of s. So here f of s is s over s square plus 9, and you know the inverse Laplace transform of this function. So the inverse Laplace transform of f of s, that is inverse Laplace transform of s over s square plus 9, using your standard formula it is given by cos of 3t, and cos of 3t will become your f of t here. So this is f of t, the inverse Laplace transform of f of s. Now I want to find the inverse Laplace transform of 2s over 4s square plus 9, and note that the 4s square I can write as 2s square plus 9. So the only difference in this f of s and this function is we have multiplied our variable s with the 2. So therefore, if this is f of s, so this function will be f of 2s. So to find this inverse Laplace transform, we are going to use this property. So here a is 2, so therefore its inverse Laplace transform will be given by 1 over a, that is 1 over 2, to f of t over a, that is t over 2. And you have your f of t here, so just replace t with the t by 2 in this function, and you are going to get 1 over 2 cos of 3 t by 2. So in this way we find the Laplace inverse of this function using the inverse Laplace transform of this s over s square plus 9. So in this way the change of scale property work. You can take different problems to find inverse Laplace transforms by using change of scale property. Now let us move to our next property. Now we are going to consider the inverse Laplace transforms of derivatives. It says that if you know the inverse Laplace transform of your function, say f of s, and is given by f of t, then the inverse Laplace transform of the derivative of f of s, so I am writing it as f prime s, that is d by ds of f of s, is given by minus t f of t, or you can write as minus t inverse Laplace transform of f of s. And this result directly follows from the result of Laplace transform where we used the multiplication by t, as you know that if the Laplace transform of f of t is given by f of s, then the Laplace transform of tft is given by minus f dash s. So if you take inverse Laplace transform on both sides, you get this result. Now let us take one example to illustrate the use of this property. So let us consider, I want to find the inverse Laplace transform of the function 1 by 2 log of s square plus b square over s square plus a square. So I want to find the inverse Laplace transform of this function, and as you see, your function involves logarithm function and it is not directly available in your standard formulae. So we are going to find this by using this property. So let us take this function as f of s, 1 by 2 log of s square plus b square over s square plus a square. And to get rid of this function logarithm, I will take the derivative of f of s with respect to s. And for that, you can write this as 1 by 2 into log of s square plus b square minus log of s square plus a square. Now when you differentiate this function with respect to s, you get f dash s, that is d by ds of fs, and 1 by 2 is scalar here. The derivative of log of s square plus b square is 1 over s square plus b square into derivative of s square plus b square, that is 2s. So therefore you are going to get 2s over s square plus b square. And similarly, the derivative of this function is 2s over s square plus a square. And here 2 is cancelled out, and you are going to get s over s square plus b square minus s over s square plus a square. Now you note that you can easily find inverse Laplace transform of this function, which is derivative of f of s, because you know the inverse Laplace transform of these functions. So the inverse Laplace transform of f dash s is equal to the inverse Laplace transform of this function, and you know that the inverse Laplace transform of this function is nothing but cos of bt minus, and the inverse Laplace transform of this function is cos of at. So this will be your Laplace inverse of f dash s. Now use this property. So we have that the inverse Laplace transform of f dash s is equal to minus t inverse Laplace transform of f of s. And now this part is known to you, and our aim was to find inverse Laplace transform of f of s. So that will be find, or you can find it directly from this expression. So when I put the inverse Laplace transform of f dash s here, I get cos of bt minus cos of at is equal to minus t inverse Laplace transform of f of s. So from here you get the inverse Laplace transform of f of s. So therefore the inverse Laplace transform of f of s is given by just take t to the other side and adjusting the negative sign, it becomes cos of at minus cos of bt over t. So this is the required inverse Laplace transform of this function 1 by 2 log of s square plus b square over s square plus a square. So by using this property, if the inverse Laplace transform of function is known, then you can find the inverse Laplace transform of its derivative, and if the inverse Laplace transform of derivative is known, then you can find the inverse Laplace transform of the function itself. And this property is very useful property we are going to use in the applications of inverse Laplace transforms and Laplace transforms. Now let us move to our next property. The next result we are going to use is the inverse Laplace transform of integrals. That is, if you know the inverse Laplace transform of your function f of c, and say it is given by f of t, then the inverse Laplace transform of the integral of f of s from s to infinity is given by f of t over t, and this result directly follows from the result of Laplace transforms, as if the Laplace transform of f of t is f of s, then the Laplace transform of f of t over t is given by the integral s to infinity fs ds. So if you take inverse Laplace transform on both sides, you will get this result. Now let us use this result to find inverse Laplace transform of one function. Our aim is to find inverse Laplace transform of s over s square minus 9 whole square. So to find the inverse Laplace transform of this function, I am considering this function as my f of s. So take this function as f of s, s over s square minus 9 whole square. And you note that this function is again not available in your standard functions or standard formulae. So what do we do here? We consider this integral s to infinity f of s ds, and this integral is nothing but the integral of s over s square minus 9 whole square from s to infinity. And if you integrate this function, you can easily see the differential of s square is 2s ds, and you can easily multiply and divide by 2 here, so that its integral is 1 by 2 into s square minus 9 power minus 1 over minus 1, and the limits from s to infinity. And note that when s approaches to infinity, because of negative sign in the power, this will approach to 0, and when you take s is equal to s, so it will be equal to 1 by 2 into s square minus 9. So this is your function f of s, and its integral from s to infinity is 1 over 2 s square minus 9. And you can easily find the inverse Laplace transform of this function. So therefore, the inverse Laplace transform of s to infinity fs ds is equal to the inverse Laplace transform of 1 by 2 s square minus 9. And you have a standard formula of inverse Laplace transform of a over s square minus a square. So if you take a is equal to 3 here, or you may write it as 1 by 2 into 3, the inverse Laplace transform of 3 over s square minus 3 square. And you know the inverse Laplace transform of this function. This is nothing but the inverse Laplace transform of hyperbolic sine 3t. So this is the inverse Laplace transform of your integral from s to infinity f of s ds. So now let us use this property here. this is your Laplace inverse of s to infinity fs ds is given by 1 over t f of t, and f of t is inverse Laplace transform of f of s. Now let us substitute our expressions here, so you can easily find the Laplace inverse of f of s, which is your this function. So if you use inverse Laplace transform of your integral, we get 1 by 6 hyperbolic sine 3t is equal to 1 over t, the inverse Laplace transform of f of s, and the inverse Laplace transform of f of s is required, as f of s is s over s square minus 9 whole square. So therefore the inverse Laplace transform of f of s is equal to, taking t to other side, it is 1 by 6 into t sine hyperbolic 3t. So in this way we have found the inverse Laplace transform of this function using inverse Laplace transform of its integral. So these were the inverse Laplace transforms of derivatives and integrals. Now let us move to our next property. The next result we are going to discuss is the multiplication by s. Multiplication by s. And this result says that if you know the inverse Laplace transform of f of s, say it is given by f of t, and the value of f at 0 is also 0, then the inverse Laplace transform of s times f of s will be given by the derivative of f of t, that is f dash t. And this result directly follows, as you know that if the Laplace transform of f of t is f of s, then the Laplace transform of f dash t is equal to s fs minus f of 0. We are using the Laplace transform of derivatives of functions, and in this case we have taken f of 0 is equal to 0. So when you invert here, you get the inverse Laplace transform of s fs is equal to f dash t, which is our result. And also note that if f of 0 is not 0 in this case, so let me write here, if f of 0 is non-zero, then again, as you know that the Laplace transform of c delta t, where c is any constant and delta t is your Dirac delta function, is nothing but c. So therefore the Laplace inverse of c is c delta t, and if you invert here by keeping f of 0 non-zero, you get the inverse Laplace transform of s fs minus f of 0 as f dash t, and this can be written as inverse Laplace transform of s fs minus inverse Laplace transform of f of 0, and since f of 0 is constant, so its inverse Laplace transform will be f of 0 into delta of t. So that will be given by f dash t. So from here you can write inverse Laplace transform of s fs, which is f dash t plus f of 0 delta t. So this result can be used in case f of 0 is non-zero, but in most of the cases we are going to use this result that there f of 0 will be 0. And also this result can be generalized to in general if your inverse Laplace transform of f of s is f of t and f of 0 and its derivatives f dash at 0, f double dash at 0 and so on, f n minus first derivative at 0, all are 0, then the inverse Laplace transform of s power n f of s will be given by f n t, that is nth derivative of f of t. Now let us take one example where we are going to use this result to find inverse Laplace transform of a function. So say we want to find the inverse Laplace transform. It is given that the inverse Laplace transform of 1 over s square plus a square is 1 over a sine of at. Using this, find inverse Laplace transform of s over s square plus a square. So you note here, to find inverse Laplace transform of this, from this result I keep my f of s as 1 over s square plus a square and its inverse, which is given to you, is 1 over a sine of at. So I write this inverse of f of s as f of t, and when you take t is equal to 0 in this f of t, that will be sine of 0, that is 0 here. So if you use this result to find this inverse L inverse of s over s square plus a square, clearly we are multiplying this function with s here. So to get this function we have to multiply your f of s with s. So therefore the inverse Laplace transform of s f s is equal to f dash t, that is d by dt of f of t, because f of 0 is 0 in this case. So therefore we have a result of inverse Laplace transform of s over s square plus a square, because this is your s into f of s, is given by d by dt of f of t, and f of t is your 1 over a sine of at. And you know the derivative of sine of at, that is equal to cos of at into a, and here a get cancelled out, so that you get the inverse Laplace transform of s over s square plus a square. As you know, it is cos of at. So we have used this example to illustrate this result, that how to use this result. So whenever you multiply your function f of s with s, you can use this result provided the conditions are satisfied. Now let us move to our next result, that will be division by s. So here I am writing our next result, that is division by s. So it says that if the inverse Laplace transform of a function f of s is known, and say it is f of t, then the inverse Laplace transform of f of s divided by s will be given by the integral of this function f of t from 0 to t, and this result is an outcome of the result from Laplace transform of the integrals. As you know that if the Laplace transform of f of t is f of s, then the Laplace transform of its integral from 0 to t f of t dt will be given by 1 over s f of s. So here, if you take inverse Laplace transform on both sides, or if you invert here, then you are going to get this result that the Laplace inverse of f of s over s is given by 0 to t the integral of f of t dt. Now let us take one example on this. We are going to find the inverse Laplace transform of 1 over s square into s square plus 4, and to find this inverse Laplace transform I am going to use this result. Now note that the same inverse Laplace transform can be found by using different methods like partial fraction, or there are other ways also, and you can go in that way which is suitable for you, but I am illustrating the use of this result, so I am going to find it by using the same result. Now to use this result, it is clear that if you take your f of s as 1 over s square plus 4, whose Laplace inverse is known, then this f of s is divided by s square. So I am going to use this result twice to get this inverse Laplace transform. Now let us start by finding inverse Laplace transform of f of s, which is your 1 over s square plus 4, which is s square plus 2 square. So its inverse Laplace transform is known to us and is given by 1 by 2 sine of 2t. Now this function will work as your f of t. So the inverse Laplace transform of f of s is known and is f of t. So therefore, by using this result, the inverse Laplace transform of 1 by s f of s will be given by the integral 0 to t of your function f of t, which is 1 by 2 sine of 2t here. And you know the integral of this sine of 2t. 1 by 2 is constant, so I write it as it is. Sine 2t, the integral is cos of 2t over minus 2, and the limits are from 0 to t. So when you put the limits here, you get cos of 2t. When you put t is equal to 0, it is 0, and when you take t, it will be cos of 2t itself. So it is equal to 1 by 4 into 1 minus cos of 2t after putting your limits. So this is the inverse Laplace transform of 1 over s into s square plus 4, because your fs is 1 over s square plus 4, and it is 1 by 4 1 minus cos of 2t. Now to get this inverse Laplace transform, we are again going to divide this f of s with s, and let us see what is the Laplace inverse of this function. So again, by using the same result, we write that the inverse Laplace transform, by dividing it again with s, we get s square into s square plus 4 will be given by the integral of inverse Laplace transform of this function, which is this 1 by 4, 1 minus cos 2t. So it is equal to the integral from 0 to t 1 by 4 into 1 minus cos of 2t dt. And you can easily integrate this to get your result. So 1 by 4 is fixed number, integral of 1 is t, integral of cos 2t is sine of 2t over 2, and the limits are from 0 to t. So when you put upper limit t, this expression will be as it is, and when you take the lower limit 0, this term will be 0, again sine 0 is 0, so all the terms will vanish and you are going to get your final result as 1 by 8 into 2t minus sine of 2t. So in this way you have used our result to find the inverse Laplace transform of this function 1 over s square into s square plus 4, which is coming to be 1 by 8 into 2t minus sine of 2t. So these were two important results, that is multiplication by s and division by s. Now towards the end of this lecture, I am going to use another method to find inverse Laplace transform of functions. So let us discuss that method, and that method is power series method. So let us see what this method is. It simply says that if your function, which is f of s, whose inverse Laplace transform is desired, can be expressed as a power series of negative powers of s, which will be of the form a naught into 1 by s plus a1 into 1 by s square, a2 into 1 by s cube, and so on, of this form, then we can invert term by term to get its inverse Laplace transform. As you know, the inverse Laplace transform of 1 over s power n, this will be a naught, its inverse will be 1, a1, its inverse will be t, and so on, its inverse will be t square by 2 factorial, and so on. So this is the way power series method work. Now let us illustrate this with the help of one example. Let us try to find inverse Laplace transform of the function I am taking as e to the power minus 1 by s over s. So it is not easy to find inverse Laplace transform of this function using ordinary methods. Now let me explain with the help of power series method. So clearly here e to the power minus 1 by s is there, so I am going to use the Maclaurin series of e to the power x, or you can say e to the power minus x. So for that, if you use this series here, your function of s 1 by s e to the power minus 1 by s can be written as 1 by s as it is. Now using Maclaurin series of e to the power minus x, it will be 1 minus 1 by s plus 1 by 2 factorial into 1 by s square minus 1 by 3 factorial into 1 by s power 3 and so on. And when you take this x inside, this becomes 1 by s minus 1 by s square plus 1 by 2 factorial into 1 by s power 3 minus 1 by 3 factorial into 1 by s power 4 and so on. So this is your given function 1 by s e to the power minus 1 by s when expressed as a power series. Now when you invert here, you find the inverse Laplace transform of this function. So this will be given by the inverse Laplace transform of this series. And as you know that the inverse Laplace operator is linear in nature, and you know the inverse Laplace transform of 1 over s power n. So here n is integer in all the cases. So the inverse Laplace transform of 1 by s will be 1 minus 1 by s square. The inverse transform is t plus 1 by 2 factorial into the inverse Laplace transform of 1 by s power 3 will be t power 2 over 2 factorial minus 1 by 3 factorial into this will be t power 3 over 3 factorial and so on. So this is the inverse Laplace transform of your function. Now let us recognize this series, or let us write it in another ways so that it is recognizable. So this can be written as 1 minus, see here I am writing it as 2 root t power 2 over 2. So it is nothing but t again, plus 2 root t power 4 over 2 square into 4 square, and sorry here it will be 2 square minus 2 root t power 6 over 2 square into 4 square into 6 square and so on. So this is your this series represented in this form. Now clearly if you see this series, it is of the form 1 minus x square by 2 square plus x4 by 2 square into 4 square minus x6 by 2 square into 4 square into 6 square and so on. And we have already used this series in the lectures of Laplace transforms. So it is recognizable, and it is nothing but the series of Bessel function of order 0. So it is j naught x. So therefore this inverse Laplace transform of 1 by s into e to the power minus 1 by s is nothing but j naught of, instead of x we have 2 root t. So this is the inverse Laplace transform of your given function. So in this way, this method, that is power series method, work to find inverse Laplace transforms of different functions. Now this is all in this lecture. In the next lecture we are going to discuss one very important result of Laplace and inverse Laplace transform, that is convolution theorem. So we will see what is convolution and how to find Laplace or inverse Laplace transforms in convolution of different functions. Thanks for being with me. Thanks for watching. Keep watching and keep sharing. Thank you.